Hey, Sam here. Let's do another daily Leetcode question. If you're new to the channel, I act as a tech interview candidate. I talk about the different approaches to solving a question, not just trying to get the best answer straight away. I have a timer here in the top left, which I'll start now. So we're doing number 1208. Get equal substrings within budget. And this is a medium question. I'd say this is appropriate level for a lot of interviews, right up until senior level or so. Honestly, even beyond. There's not really too many reasons you go to hard questions. So let's expand this and see what we have. We're given two strings and we're trying to find same length and an integer max cost. You want to change s to t. This makes me think of the Hamming distance, which we did recently. So the idea is we're trying to change characters in the same index between the two arrays, s of I and t of I, and the cost to change it is the difference in the ASCII values between the two characters, and we're giving an integer max cost. So return the maximum length of the substring of s that can be changed to be the same as the corresponding substring of t with a cost less than or equal to max cost. If there's no substring from s that can be changed to its corresponding substring from t, then return 0. This makes me think of, so I'm already starting to think about how I would approach a problem like this, and we're trying to find a substring between the two arrays. So here we have A, B, C, D, and B, C, D, F, and we're trying to find the maximum length, not even what the values are, just the maximum length of the substring between the two of them that can be changed with a max cost less than or equal to max cost. So here ABC could be changed to BCD because each of them is only one character off. So 1, 2, 3, and that's max cost of 3 less than or equal to. So we have max length of 3. D to F would be D, E, F. So that'd be 3 by itself, but that length is only 1, so we don't want to do that. Here we have A, B, C, D, C, D, E, F. The max cost is still 3, but A to C is 2, and B to D is 2, and so on. So each of them is 2, so we can only do one of them. It doesn't matter which one. And then finally, here A, B, C, D, and A, C, D, E, max cost is 0, so we can't do any changes. And it's not 0 because the A's are the same. So we do need to keep that in mind. Kind of some questions I have is whether the start and end strings, the S and T strings are different lengths. What would we do then? But we don't have to worry about that. They're always the same. They fit in memory, less than 10,000, 100,000 characters. The max cost fits in integer space, so we don't have to worry about summing up all these values. Only lowercase English characters. So yeah, this seems pretty fun. I think kind of what I'm thinking about, and I'll get to it too, we'll call that approach 2, is something called a sliding window, which I think you may have heard of before. I'll get to that in a second, but let's just start with the brute force. If you don't have much time in an interview, I would kind of talk with the interviewer and say, like, here's what I'm thinking about. I'm pretty sure the sliding window approach will be the one I want to go with. The brute force approach is every pair of start and end indices, calculate cost, and keep best length. So here, every pair would be a O of n squared for n characters to find the start and end every pair possible, and calculating cost that way would be a O of n. So the total would be a O of n cubed, which is very inefficient. So let's not even worry about trying to implement that for now. The nice thing about a sliding window, and the idea here is, let me see if I can just, well, yeah, I'll keep it like this. So the idea is if you have your array, let's call it A, B, C, D, E, you start with your start indice and your end indice, and we'll call them A and B, and they're both equal to 0. And you just start trying to grow out as much as you can until the cost is greater than the max cost. And then at that point, you start retracting the beginning. So let's say you had ABC, now you'd retract the A and you just have BC. Then you try to again expand outwards. And if you can, you're good. And if you can't, you have to retract. And you just kind of keep inchworming your way across, keeping track of the best cost and length as you do. And the nice thing about that is you're iterating 2 indices over the array. This one has a in time O of 1 space. Sorry, just jumping back for a second. You're iterating through the list just once for both indices. There's no multiple pairs or anything like that. So it's O of n to iterate. And the real nice thing about this is because you're only ever adding or subtracting one index at a time, and you're only going to do it once for the whole array, it's O of 1 add some, let's call it expand retract. The cost, the O of 1 time to expand retract, and you're only going to do that over the array. So this becomes a O of n time and O of 1 space approach. And there's nothing better than that. In the ideal case, you have to check over every single string. You can't really skip the last half once you've hit certain length. For example, you don't know if there's a better length later on. So this is as optimal as you can get in terms of big O complexity. So I'd say this is good enough. How much time are we in? 5 minutes and 33 seconds. So I'd say that's a good time to start. All right. So how do we do this? I'd like to create two indices. Actually, that was just as is, like that. Oop. And while we're within the array, while b is less than n, while a is less than n and b is less than n, we want to iterate over this, and I'd like to do this in two parts. If we can expand, else retract. And during this, we want to keep track of our best length. And initially, our best length is 0. Is that true? Technically, yeah, it is 0. Let's say A inclusive, B exclusive. So this works the same way as normal array operations. So when A and B are both the same, that means that you have a 0 length array, and the best length is 0 at that point. So if we can expand, otherwise we retract. So if b plus 1 is less than or equal to n, so we're able to expand. So b plus 1. What I'm trying to do here is also keep track of the current cost. So current cost is equal to 0. If we can expand, sorry, the reason I'm getting hung up is how I'd want to do this. Okay, so we can do it one way. This is not the way I think I like the best, but if b plus 1 is less than or equal and the current cost plus the cost for b, which let's just say that's the absolute value of the difference between, they're called s and t of b plus 1 minus s of b plus 1. These are strings though, so we need to turn them into ASCII values, or the integers values. We're doing the absolute because that's the difference between the two of them. If we can expand it, and that is less than or equal to max cost, then we're able to expand b, and we can also add that current cost. The reason I don't like this is because I think it's going to get messy in a little bit, but I want to get some code up and we can try to optimize it as we go. So here the idea is if we're allowed to expand in array and less than max cost, then we expand. If we are not allowed to expand, we have to retract a. So here, a plus 1, the current cost here, I'm just subtracting a. So this is the general gist of it, and then we return best length, which we haven't even done. There's a lot of edge cases where I think this is going to start to fail, which I'm not happy about. That's kind of why I'm pausing as I'm talking. So here the idea is if we expand, we can say best length plus 1, because we just, oh, not best length plus 1. Best length equals the max of best length and b minus a. B is not inclusive. Sorry, B is not inclusive. Because B is not inclusive, we have to use the one that's before it. That's why we're doing less than or equal to. And then B minus A. Here's the problem though. We've retracted A, but now if A has increased and B has not, then it'll start to fall apart. So we could do something like if A is greater than B, greater than or equal to B, B plus 1 also. And then we have to add if B is greater than or equal to N, we break essentially. Otherwise, we have to add the current cost of B. And then we also have to do a check to see that that's even yeah, this gets super messy. I don't like this very much at all, actually. Okay, the reason I'm getting kind of hung up is because we're trying to increment A and B, and I think what I'm realizing is, this may be obvious to several of you, and this is why you should practice your sliding windows. You don't actually have to decide between A or B like this. I think you can just increment B constantly. So let's clean this up first. I'm keeping this. I'm gonna come back to that in a second. So let's keep this over here, and I'll pull this as I need. So the idea here is I want to keep incrementing B. I'll always be expanding. So the current cost. Let's go backwards. This is a bit too messy. Let's make both of these inclusive. I think that'll actually simplify things a bit. And what that means is that we are calculating the current cost plus the absolute value of the order of T of B minus the order of S of B. So we always add the current cost. Then we have to retract A until valid, while current cost is greater than max cost. A plus 1, current cost minus the value that we just removed. There we go. And then we are expanding otherwise. What happens, I think, and then the best length is equal to max of best length and the current B minus A plus 1 because we're inclusive now. So we retract until valid, and we are always expanding B. And this should be a lot cleaner, actually. I like this a bit more. But what happens if A gets bigger than B? Is that possible? What if the current cost is always greater than the max cost? Then A plus 1. Actually, that's fine, because now if A is bigger than B, then this will be a negative number. And no matter what, it'll never replace best length, so B will just increase by default. Okay, I like that. I actually like that a lot. So let's try, hopefully everyone's seeing this. Yeah? Okay, cool. So let's clean this up. We don't need that brute force approach anymore. I don't like this double length. Let's clean that. Oops, sorry. Okay, so this is the whole code, and this is kind of why I was struggling, because I remember sliding window does not need to be too complicated, and it's really easy to get stuck, as you just saw I did there. I think this should work. I'm trying to think of, let's run through some edge cases, better than saying I think this should work. So let's think about A, B, C, D, B, C, D, F. So right now it starts at 0, 0, best length 0, current cost 0, both indices at the beginning. It starts at A and B. The current cost gets incremented by the current B, which is 0, so it adds in whatever the difference of A and B is, which is, in this case, let's actually just A, B, C, D, B, C, D, F. The current cost will be 1. So let's say difference between A and B. Like that. And then while the current cost is greater than max cost, it's not, so we don't increment A. Best length is now equal to 0 minus 0 plus 1, so that's 1. And the best length is 1. That's great. B just becomes 1 now. E equals 1, A equals 0. So now it does the same thing. It adds the second one, B and C. The difference between that is 1. So current cost now is 2, which is still less than max cost, so it doesn't decrement A at all. Best length incremented is 2 now. We come around and now B and, so let's just put that there. B is 2 now, so we're at C and D. Current cost becomes 3, which is still less than max cost, or less than or equal to max cost. So we still don't decrement. We go to the next one. B is now equal to the third indice, and 0, 1, 2, 3, D and F. The current cost becomes 4, and that is too big. 4 is greater than 3, so we subtract the value at A, which is A is 0 still at this point. So the current cost now becomes 3, A becomes 1 and 3, and we are still valid. B plus 1, we've reached the end of our array. The best length has been 3, and that is correct. So I think we're good there. I want to add an edge case also where we have no possible valid value. So let's just call this Z, 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 Z. And max cost is 3, showed that. That one should be 0. If that was the case, we keep incrementing A until we reach the end of the array, because no matter what, current cost plus 1 will be, and then you have to subtract that value. So A becomes B, or is greater than B, so it'll be 0. Best length will still be 0. All right, let's try that. Testing, runtime error, because n doesn't exist yet. Apologies for that. N equals the length of S, which is equivalent to the length of T, because we are assumed that they will be the same. Okay, let's try that again. All right, great. It got those test cases accepted. Happy to see that. It passed the one where it was supposed to be 0. I'd like to create another test case, actually, where I'd like to create one where it's a single length string, and let's create it like that. I would expect that to be 1. And then one more for where it's invalid and then becomes valid later on. So let's call this like Z, sure. And the difference between these one will be FF, G, 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 Z. And the max cost can only be 1 or 0. So here I want it to be 1 at the end, and I want to make sure it gets to the end. I think it will. Good. Passes those test cases. Here that was 1 for a single length string, and here max cost 0. It still gets you 1 because of the last value. I'm just kind of checking for these edge cases, and I want to make sure they pass. So let's, this is looking good. I'm feeling pretty good about this. All right, let's try submitting this and see what we get. All right, fingers crossed. Come on. Yes. And completion streak, 1 day. I don't do these every day, but it is awesome. We're in the bell curve. We're doing pretty good. I see there's possibly some optimizations there. We definitely need to see what we can do there, but very happy to see that I submitted and passed in the first go. So that's awesome. Let's have a look at what we could do to optimize this a bit. There's a couple things I'm thinking about. Number one is I really don't like having to... One of the things I've been thinking about was converting these strings into integer arrays straight ahead of time. So let's just say like si is equal to map int or ord of s, something like that, and you create a list of that. And then when you do the checks, they're just direct subtractions. You don't have to do it each time, but this would become an O of n space solution. So I don't actually think that would be any faster. Double while loop is scary, but because it ends when it ends within the end loop. This is still O of n no matter what. I don't think that's a problem. I wouldn't worry too much about the timings because this bell curve is within 10 milliseconds, 20 milliseconds, and that's just the back end of the Leetcode. There's a lot of variance. I could easily see us being somewhere around here. I can't think of anything that would algorithmically optimize this at this point. Let me know in the comments if you see anything. This is kind of an interesting one. I think we are pretty close to optimal. I'm pretty happy about it. Let's have a look at some of the other solutions and see if there's anything there. So here we have this one, and it does the same thing as us. That's good to see. It does an if-else check, and it calculates the length only when the cost is not greater than the max cost. Let's see if we do anything different there. So they don't do a double while loop. I think that might be one. They do an if-else check and just have the main loop do it. Maybe we have less of a stack that way. I don't know. I'd say to me, these both feel equivalent mathematically and algorithmically, so I wouldn't expect that to be any faster. Okay, how about over here? It's about the same thing. They do calculate the costs once ahead of time. I like that a lot, actually. That is kind of nice. This does become an O of n space solution, though, so I wouldn't say this is algorithmically more efficient in terms of space complexity, but in terms of pre-calculating all at once, there's some backend optimization, I'm sure, in the Python interpreter that deals with this, that makes this faster, so I do like that very much. Okay, overall, pretty happy with this question. I thought what we got to was pretty awesome. So hopefully this was interesting to everyone watching. Let me know if you saw anything as you got there, anything that tripped you up. Thanks for watching and see you all next time. Cheers.